So you have seen the plan. Moreover, the plan is sent to you, was sent to you. If you have not received the plan, it means that you are not registered. So please register. If you don't know where, I'll tell you. But now, let me put in some details. Okay? So in algebra geometric correspondence, the figure is a solution to the set of equations. So you know what mathematicians decided. They decided that you do not need to solve these equations. It is enough to consider all consequences of these equations, just if these equations were solved. And say that in the algebra, say, of polynomials, these equations and all their consequences vanish. So from this set, we have consequences. So if this is zero, then this is zero. So how can we characterize this property? The space of all expressions of this type. We can characterize it by the following property. If we multiply it by some polynomial, you will still be in the same set. And it is called ideal. So that is how you should think about it. But there is also, of course, a concise definition. So ideal is, is a subspace of A with the following property. If A belongs to ideal and B belongs to A, then AB also belongs to ideal. And also E is a subspace of A as a linear space. So here I somehow explain two ways of thinking. This is axiomatic way. This is how it looks like. And we consider the ideal as a space of functions, polynomials that vanish at a figure. And we associate with a figure. Important property, note. That the classes of conjugacy of A over I is also an algebra. So A over I means that we consider classes of the following form. Class of A is actually a set of A plus, or maybe I will call it B, of B plus A, where A belongs to ideal. So you may think of B as the space of functions on the figure. Because actually, the value of the functions or restrictions of the functions to the figure is independent on A. Because A is an ideal. An ideal is something that vanishes on figure. Okay? So that's why it's not a surprise that these classes are natural. Moreover, this is a definition of these classes as a coset linear space. But they also form an algebra, actually. Class of B1 could be multiplied by the class of B2. And what you should do? Take some representative. B1 plus A1. B2 plus A2. A1 B2 plus B1 A2 plus A1 A2. And all this belongs to ideal. So multiplication of classes does not depend on representative. And that's very important. By the way, let me ask you, do you remember that in group theory, there is a similar construction? However, group theory is non-abelian. Therefore, in group theory, there is a special additional condition on what you divide on. Who remembers the name of this condition? Do you remember when G over H is a group? H is a subgroup. Do you remember condition on H? Then, of course, you remember. I'm asking people who consider themselves as physicists. Who came from physics. Let us see the example. Suppose G is SU2. Suppose H is U1. What is G over H? Who knows? Tim, you are saying something. Tim. Tim, please, if you want to say something, turn on the voice. You see, I'm sorry for delaying, but I'm actually looking for the back reaction because I need to know what do you, Tim, if you are saying something, I don't hear you. Ah, so there's a chat. Ah, you prefer chat. Sorry. Okay, great. Great. So, since this is commutative algebra, we do not need this normality condition. Very well. So I'll go faster. You see? I am really afraid that I will lose you at some moment. I don't want to lose any of you. You see? That's why sometimes I am too slow. So I just need to know your level. Actually, I would like to know the level of the rest because I already know Tim and already know who. I mean, Miss Who. I actually want other people to say something. Okay, so for Miss Who, SU2, it's a unitary group who is okay, say matrices 2 by 2 with determinant equal to 1. So this U1 is not normal in SU2. That's why SU2 over U1 is topologically a two-dimensional sphere, and it is not a group. So actually SU2 is almost like SO3. They are rotations in three-dimensional space. And if you say that you are interested only in direction of rotation and not on the angle, you may factorize U1. So actually, what you have here is S3, S1 over S2. So I'm explaining why it's U1 geometrically. So rotations come from the axes and angles. When I factorize U1, I'm factorizing with respect to this angle rotation. Then I have the space of axes. The space of axes is determined by points where these axes hit the two-dimensional sphere. That's why it's two-dimensional sphere. We need to keep up orientation, etc. So actually, would I take here SO3? I will get not S3, I will get RP2. Okay, but in any case, these guys are not groups. So here we do not have, here normality is obvious. You may multiply from the left and from the right since multiplication is commutative. And it makes life easy. Normality would appear if we go to non-commutative geometry that is developed right now. Okay? That's not developed. That is developing right now. It is not developed yet. So now people do it. Okay. Now there are several important notions. last important notion is the following. Before I do this, let me try to explain the picture that has. So we started with what I call space, and there is figure, and there is also figure 2. So on its own, any figure may be considered as a space. You see, I told you that that we are interested in so we study figures in space, okay? But you may ask if a figure is a space on its own. And the answer is, of course, yes. It was exactly the content of the theorem, that if you have an algebra that corresponds to space, and if you have the figure phi inside space, then A over I phi is exactly the algebra corresponding to subspace. So, so here is democracy. It means that everybody could be a boss. Okay. So here, this space is a boss. Everything belongs to him or to her. Okay. However, if you take a quotient, then this figure is a space itself. So it is exactly what people realized in the 19th century. So they started with R3, and they saw that it is a space. They realized that say sphere is clearly a figure. Okay? Because it's given by equation x squared plus y squared plus z squared equals to 1. So it is a space, it is a figure. Then people thought, okay, it's the Earth. So it could also be considered as a space. I can draw something in it. So Earth could be, the surface of the Earth could be considered as a space. In this way, we have curved planimetry. But what's more important, we may consider our space where we live not as something given, something special, but also as a figure somewhere. So to be a space or to be a figure, it is the same. So it is like in the army. You are simultaneously a boss and a soldier, okay? You get orders and you give orders. So it is the structure. And this structure is called geometry. Okay. So after I commented, by the way, it took people a lot of time to realize that our space could be a figure somewhere or an abstract figure, okay? It was not obvious. Okay, now let us come to the issue of what we can do with ideals. So when I speak about ideals, I actually have figures. So suppose I have ideal 1 and ideal 2. I can multiply them. Okay? I consider I1 times 2 as y1 times y2. So what does it mean? It means that elements of this product are elements of the type A1, A2, linear combinations. I call it span, where AI belongs to II. I goes from 1 to 2. Now, what can we say about the figure 1, 2? That corresponds to the product of ideals. So let me ask Tim. Tim, don't you mind if I will ask you sometimes? After all, you are my compatriot. And as you know, русские своих на войне не бросают. Tim, is it okay that I'm asking you? Great. So suppose I have 2 figures. To each figure I have an ideal. I create new ideal by taking a product. Very good, Tim. Very good. So Tim writes that phi 1, 2 is phi 1 unified with phi 2. Actually, naively thinking, we may ask, where does this thing vanish? So it vanishes if one of these two vanish. So since I'm considering the vector spaces, linear spaces, they are overfilled, so they have no divisors of 0. So would it be points? Would it be points? The figure where this vanishes considered is actually a union of these two. However, we need to put this thing in this question mark. Let me give you an example. Polynomials modeled by x. Okay, so no, I'll put it this way. Suppose ideal is x is a set x times polynomial of x. It's clearly an ideal, okay? So what corresponds to this ideal? A point. This figure is a point at x equal to 0. then what if I take I squared? So would it be ordinary or union? I would think that it would be 0.0 union with 0.0. Okay? And this is in set theory. It is again 0.0. Okay? However, if I take a product of these two ideals, is x squared times p of x. And this is a double point. Okay? So basically, I would say that Tim was correct in say transversal case. However, there are subtleties. So union of point with itself is not the point. It is a double point. However, now assume that points are different. Another example. I1 equals x minus alpha 1 times polynomial of x. I2 equals x minus alpha 2 times polynomial of x. I1 times I2 therefore equals x minus alpha 1 x minus alpha 2 times polynomial of x. You see, I prefer to give explicit definition of what we are talking about. So I1 times I2 vanish. Definitely on the union of points alpha 1 and alpha 2, right? So actually, in general case, we may call it transversal case. It's a union. But then let us move alpha 1 to alpha 2. So union of these two things becomes something that is not a union. It's interesting. So in this way, we are improving definitions, okay? We are going from set theoretic union to proper union. You see, in this way, algebra dictates geometry new notions. I think it's interesting. Okay? So, let me tell you what is great about algebra geometric correspondence. It is actually correspondence between logic and imagination. When you say algebra, it's logic. When you say geometry, it's imagination. When you have this correspondence, you identify logic and imagination. Some things are understood easily from the point of view of logic. Some things are understood easily from the point of view of imagination. Proper understanding is the connection between them. And this connection is done by algebra geometric correspondence. Like here, when alpha 2 goes to alpha 1, you have a feeling that second point is not disappearing when it comes to the first point. It is geometrical feeling. However, this geometrical feeling is, you see, comes to this very natural axioms, because this set of axioms are natural from algebraic point of view. Okay? So what we see the geometrical feeling and naturality of algebraic structures give the same thing. And this is the understanding. Is it clear what I said? So, people, if you will ask questions, it would help. Yes, Tim. We have to think of figures not just as collection of points, like you said before. By the way, during my course, you may have an impression that I am torturing great physicists and mathematicians. One day I am torturing Newton. Now I am torturing Cantor. Okay? No, I am not torturing them. We are just doing the next step. Each discovery has its limitation. You could not discover the final structure. So some people think they can. But to discover final structure, it's just to imagine that you personally is a god, but you are not. So not being a god, you are discovering something with limitations. However, your discovery is a step, as all Chinese people know, that we are doing steps. We are not getting the final answers. We are not getting the final language. So Manin, who is my collaborator in 2 papers, says that mathematics is development of the language. And clearly it's impossible to get the final language. Only Muslims think that Quran was written on the sky. So it means that the final language is Arabic language and the text is final. Other people think that we are constantly improving language, okay? So set theory was a great discovery of these Jewish people of German culture, okay? However, it had its limitation. Then it was actually improved a lot by French school. And that's what I'm explaining right now. But even this has its own limitation. So I'll introduce languages and limitations. Okay? So actually science, it's a path, it's a way. Okay? It is very hard to understand it. So young people mostly would never understand it. They typically have idea that now I'll study it in proper language and I'm done. No, you are not done. You are studying it in the contemporary language, not in order to know it, but to see its problems and go further and further and further. And the same happens in both physics and mathematics. Okay, because physics is like geometry, and mathematics is like algebra. Okay, so even this picture by Grothendieck is not the final. Maybe sometime I will tell you why it's not the final. But at the moment I'm talking to you the French mathematics of 50s. Okay? Okay. Now another thing. So on figures we considered union and we knew how to improve it. Now what else could we do in sets? We have not only this operation, but maybe some other operation. Can someone tell me what this operation is?
Intersection?
Or something is coming. So concerning Manin, yes, Yuri Manin. If you wish, Yuri Ivanovich Manin.
Intersection?
Exactly, intersection. So on another side, we have figure 1 intersecting with figure 2. So the question is, what is the corresponding operation on ideals? We do what? So actually, in this way of teaching, I am provoking you to think, to give definition by yourself. And for people who are not interacting, you should try to do it yourself. Try to guess what would be the definition. And if you are shy, no, it's not a compliment. We will see the compliment later. But at the moment, it's not a compliment.
The sum of two ideals.
Great. Okay. So Artem Vasilkov and Tim Sullivan said that it is the sum of two ideals. By the way, could you explain to me? Okay, so maybe I would like to hear Artem. Artem, how would you explain why it is the sum of two ideals?
Because we have in sum of ideals we have elements that looks like finite sums of each of its linear combinations from elements from I1 and I2. So we need the sum equals to 0. This means that both elements from I1 and I2 should equal to 0.
Okay, great. However, as you know, I would like to say almost, and we will come to this issue, okay? So in general position, it's true. So let us look how it works. I1 plus I2. So let us consider I1. X times polynomials of X and Y. It's an ideal. You see, actually, ideals that have the form an element times all algebra are called principal ideals. Okay? So ideals that have the form A times A, so this is an ideal, are called principal. By the way, not ideals are principal ideals. So let us consider I2. Y times polynomial of X and Y. So how can I characterize I1 plus I2 in terms of polynomials? So who is brave to tell me? Maybe Tim would tell. How to characterize the sum?
All polynomials without a constant term?
Yes, exactly. Polynomials without constant term. Of course. By the way, is it a principal ideal? Polynomials of two variables without constant term. So at least Tim has okay, Miss Who. So maybe Miss Who, maybe I should call you by your name, but I'm afraid that I would mispronounce it. May I ask you to pronounce it? And I'll do my best to pronounce it.
You pronounce as eating.
Say it again, please.
Eating.
Eating. So like eating, but with N replaced by T. So eating, okay?
Yes.
So can you recognize at least what I mean? So when I say eating, you understand?
Yes. Oh, we don't pronounce the k at the end.
Eating.
It's just a yes. It's a nasal sound, but that does not exist in Russian or in English. Oh yes, it exists in English, but not in Russian.
Okay, eating.
Yes.
Okay. Well, thank you. Okay. So it's not a principal idea. By the way, could we say informally which ideals are principal or not in terms of figures? So what is the great difference between this I1 plus I2 and examples that we considered before? Okay, thank you. Exactly. You got it. So Inning says, look, the ideal is principal if this figure is the zero of one single polynomial or the element of the algebra. So it's principal if the figure could be given by one equation. To get a point or 2 points, we can have one equation. To get here the point 0 on the plane, so is it clear that this ideal corresponds to the plane with the point? Oh, sorry. And you cannot get the point of the plane in one single equation. Just try to feel it.
Are we talking about a C or about, I mean, about complex numbers or?
Okay, so let us talk about complex numbers. So let us work about this field. So this is not C, it's C squared. C squared. So this is C whose coordinate is X. This is C whose coordinate is Y. So this is the origin, 0.00. You cannot get it by one equation. Roughly speaking, because equation puts dimension down by 1. And point has dimension that's down by 2. But still it's a point. Now, what is this principle? What this principal idea? Ideal X times polynomial. So can you tell me what this is and what this is? And I'll draw these two figures. So what is X? So what is I1? What is this figure?
The X so-called axis?
Yes, so I mean this ideal. So how should I draw it?
Y-axis.
The plane that passes through x equals 0.
Okay, so it is a vertical line, yes? And this is a horizontal line. And here I have this intersection. So it means that in general situation, it is perfect. And you see that in general situation, dimension goes as it should go. Okay? So codimension plus codimension. Codimension of phi1 times phi2 is codimension of phi1 plus codimension of phi2. Do you know what codimension is? So codimension is roughly speaking dimension of the normal bundle. Okay? So normal bundle here is one-dimensional, normal bundle here is one-dimensional. When I take an intersection, normal bundle is two-dimensional. Okay? Now, let us consider the following example. Maybe somebody would be smart enough to tell me what would be the example that I'm going to consider now to see the puzzle.
The sum of ideals produced from x and x squared?
No, it's too complicated. You see, you know the subject. So here is a meta definition. You know the subject if you can construct the simplest example. Maybe I don't know the subject good enough, but we may compare the examples. You see, examples are not defined as partially ordered set. Example is a picture. Okay. It's a something informal, but it's something that
Maybe
we
two
understand.
lines coincide.
Great. We have one more point for China. Okay. Exactly. But two coinciding lines. What does it mean on the language of ideals? It is I for first line plus I. So formally it's I by the definition of ideals. Okay. So here we have a failure of the French theory. French theory, okay, Grothendieck et al. Would say that ideologically, summing I plus I should give an intersection. But here it says the intersection of I with itself is I. Okay. So set theoretically, it's correct. But geometrically, you think that intersection of the line with itself should have codimension 2 and not 1. And this is a subject of so-called derived algebraic geometry that the elements of which we will consider later on. Okay.
So you would talk about something like TOR or like this.
So actually, you need to study supermanifolds in order to understand this. But we are trying to approach them. Okay. Just remember this example. So you see, it's like talking about sex to your children. Don't be afraid. When you grow up, we will tell you. Okay. Now we will have a break. Okay. So am I going at the proper speed? So please vote. Who says that? Please vote. FA, okay, faster. It means that I should go faster, slower. keep it. It would mean move at the same speed. And of course, only those who vote are counted. So
I
please
guess we
vote.
can go a bit faster.
Okay. Tim, I get your point. Okay. I understand that you say that I can go faster, but here I get a reply for people who are active in exchange. So you see, I'm looking at the other people in the audience, and actually I don't want to lose them. So when you go to a trip, suppose you go hiking, okay? You should not think only about the strongest man in your company. You should bring all the team from point A to point B, okay? So I apologize. Okay? So let me tell you what will happen in after several more talks. Some people will drop out. And then I'll be oriented. So I am oriented on the center of mass of the audience, okay? So it's a problem of all teacher. But I gave you this problem about I plus I. And while I'm going slower than your speed, you may think what is going on. So actually this problem is the central point of the colloquium that Luria gave at Harvard. So for advanced people, it is a problem. Suppose we have CP2, okay? And you have CP1 and another CP1. So everybody knows that since CP2 is compact, intersection is well defined. So CP1 with CP1 intersect by a point. Okay? However, set theoretical intersection CP1 intersect set theoretical, yes, with CP1 is CP1. So it is with itself. Okay? So, okay. Maybe it's better to write it in the following way. So here is CP2. So CP1 alpha and CP1 beta. CP1 alpha intersects CP1 beta. So it is a slope. It's a point. Okay? If alpha is different from beta, CP1 alpha intersects CP1 alpha is CP1 alpha. Set theoretical. So you might start think what algebra geometric correspondence tells you. It tells you that I alpha plus I beta, sorry, plus not a linear algebra, is I corresponding to the point. And I alpha plus I alpha is I alpha. You see, here, algebra geometric correspondence does not teach us that something is wrong. So in this case, both algebra and geometry, both algebra and set theory fail. Okay? Do you see what I mean? Tim, do you understand the example?
Well, I guess I'm not very familiar with the complex projective planes, but the idea.
Okay, but you're familiar with lines.
Well, yeah. On this level, I get it.
Yes. You see, that's why I'm just trying to draw it in different ways. So if you're not familiar, please understand that these two lines do not intersect at infinity. Because infinity here is not one point compactification, but actually compactification by directions. And alpha and beta are directions. So at infinity, they are not intersecting. Okay, but still I know that you are not familiar with CPN.
I don't understand how this example is different from the previous examples. Because then just now we also had two lines intersecting, and we said
Yes,
that
but now we consider intersection. So we consider the following thing. We consider the product of ideals. And it was correspond to union.
Mhm.
Now we consider another operation. It is a sum of ideals.
Mhm.
It's also ideal. And if ideals are somehow transversal, it corresponds to intersection, as
Yes.
was explained.
Yes.
So very good. Now consider this example. Two lines are intersecting. So here is what set theory tells us. If alpha and beta are different, the intersection is a point. If alpha and beta are the same, intersection is the line. Because in set theory, object intersects with itself by itself. Okay?
Okay.
So it is what set theoretical geometry tells us. Here is what algebra tells us. Sum of these two ideals is ideal corresponding to a point. We already considered an example.
Yes.
Sum of ideal with itself is this ideal. So both set theoretical geometry and algebra geometric correspondence that I'm teaching
And
give the
no,
same answer.
just now we saw an example with lines, but normal lines, not projective lines. Are these two examples different?
It's a different way to draw a picture. So it is the same line. So when people that are doing projective geometry say line, they mean line compactified at infinity in the standard way.
Yes.
So when people in algebraic geometry draw lines, they're drawing it like this.
Mm-hmm.
when people who prefer differential geometry are drawing lines, they are writing this round thing, just telling you that we have a compact manifold.
Mhm.
Of course, this sphere that I drew looked more like CP1 than CP2, but I cannot draw in four-dimensional space.
Mhm.
So this drawing, this is to show that it is compact, and therefore intersection is well defined.
I don't understand this point. For example, if we consider the affine plane, then it is not compact, but we do not have a problem with intersection. Why do we need it to be compact?
Let me tell you, okay? Example. See, I'm answering, give an example. Consider XY plane. Consider two lines, not two figures. Figure 1 says y equals to 0. Figure 2 says polynomial of x okay, y equals polynomial of x.
Okay.
So let me draw it. First line is a horizontal line. Second line is something like this. Okay. So they do intersect. Now, so polynomial is a n x to the power n. Sum from n equals 0 to capital N. Okay? Now imagine that a n, the highest coefficient, goes to 0. What would happen to the root? One of the roots would go to infinity. And then the intersection dies. So for non-zero, we have n roots and capital. When highest is 0, we get n minus 1 roots. Informally, we say that root went to infinity.
Mhm.
But you see, it's just an explanation of a child. Say, where is your hat? Okay, I lost it. It's not serious to have a theory when you say why something happened. It went to infinity. Means I lost it. So grown-up people are not losing things. It means that grown-up people actually compactify. And that's why you do not have this runaway phenomenon. Nothing leaks to infinity. Intersection between, so this phenomenon is absent if the space where you are intersecting is compact. And when the lines that you are intersecting are also compact in the sense they have no boundary, then intersection is defined. That's why to define an intersection,
in the sense of Bézout, the theorem,
yes.
the theorem of Bézout, you have to consider it
Yes,
in
yes,
projective
you
plane.
see, actually, but actually, how can we save the game here? So, like 200 years ago, people say the following. Let us consider homogeneous polynomial. So ANXN is something wrong. Let us consider two other coordinates, Z, Z1 and Z0. And let X be Z1 over Z0. Then I will have this. Now, let me multiply everything by Z0 to the power n. I will get AN Z1 to the power n, Z0 to the power n minus n. Here I have the sub n from 0 to n. And now I'm studying this thing. Okay? So considering this thing actually means that I compactify by the point Z0 equal to 0. But Z0 equal to 0 corresponds to X going to infinity. However, now I know in which sense it goes to infinity. So here I have homogeneous polynomials of degree n. Okay? And I can compute solutions. And here I take into account infinities.
Mhm.
Okay, so I think now I need to stop the break, but still I want to now I'm sorry, guys, we had some discussion in between, so I need to stop for 2 minutes. By the way, Tim, have you known this argument and this reasoning? How to include infinities?
Yeah, about the homogeneous polynomials. Yeah, I heard about it. Yeah.
Okay, you see, it's my information, not on homogeneous polynomials. It's my information about you. Okay. So 2 more minutes. Sorry, guys. By the way, last thing before this 2 minutes, when I'm saying something, I actually want everybody who is present to reply immediately. We know this. We don't know this. So I will note my audience. Again, you may not show your faces. It's okay. During my talk, you can eat, watch movies, whatever. But I need any kind of back reaction. Okay? It could be in chat. It could be if you show video. It could be by voice. Non-empty reaction. Okay? So my work, because my work is measured in the amount of transferred knowledge. Okay? Okay, 2 minutes break.